Thank you. It's a great honor and a great pleasure to be here, and I'm very thankful for the invitation and thankful for the opportunity to talk to some of the young people here who are thinking about a lot of the same issues that interest me. Good. I know it's not the habit in physics colloquia for people to read from prepared text. It is much more the habit in philosophy talks for people to read from a prepared text because philosophers are particularly concerned about getting the words right and trying to say exactly what they mean. So I hope you'll forgive me for reading some of this. I know it's unusual in physics colloquia. Good. Our everyday macroscopic experience of being in the world is saturated with all kinds of temporal asymmetries, thermodynamic asymmetries, and radiative asymmetries, and epistemic asymmetries, and phenomenological asymmetries, and asymmetries of overdetermination, and asymmetries of influence, and what have you between the past and the future. And there's a long-cherished hope, something that has its origins in the work of Boltzmann, and which has been pursued by any number of other investigators through any number of fits and starts and revelations and wrong turns ever since. There's been a hope, that is, that all of those asymmetries can ultimately be traced back to some relatively simple characteristic of the initial macrocondition of the universe. The thought, as people put it these days, is that all we need to do in order to account for these asymmetries is to add to the fundamental time reversal symmetric dynamical laws and the standard statistical mechanical probability measure over the space of possible physical states, a simple postulate, a so-called past hypothesis, to the effect that the world first came into being in whatever particular low entropy macro condition it is that the normal inferential procedures of cosmology are eventually going to present to us. The business of working this thought out in detail is a very big undertaking. It's still very much in its infancy, and it's still very much the topic of lively debate. And I don't want to attempt anything along the lines here of a sort of a comprehensive overview of that project. All I want to talk about today is a certain widespread and fundamental and perennial kind of puzzlement about how it is that a project like that could even seriously be entertained. A puzzlement that is about how it is that the macro condition of the universe 15 billion or so years ago, all by itself, could even imaginably be up to the job of explaining so much about the feel here and today and on Earth of the passing of time. The puzzlement has a number of different forms, and it arises in a number of different contexts. On the most trivial level, there's a question about how the lowness of the entropy of the world 15 billion years ago can impose any genuinely profound and vivid constraints whatever on what the world is doing now. And all that needs to be said in order to make that sort of puzzlement go away is that although 15 billion years is a long time, the entropy of the universe at that time was very, very low. And in particular, 15 billion years is a great deal shorter than the expected relaxation time of the state in which our universe seems to have started out. So that's all one needs to say about the first version of that puzzlement. But there's a somewhat more interesting question in the general vicinity of this first one about how the lowness of the entropy of the world 15 billion years ago can have any genuinely profound and vivid effects or impose any genuinely profound and vivid constraints on what particular localized human scale quasi-isolated subsystems of the world are doing now. The worry in particular runs like this. Let it be stipulated that the standard Boltzmannian arguments do indeed establish that the overall entropy of the universe, which starts out in a low entropy past hypothesis sort of macro state, is overwhelmingly likely to rise toward the future. People are fond of pointing out that that tells us nothing at all in and of itself, and considered as a purely logical matter, about the behaviors of the entropies of quasi-isolated subsystems of the world. Just as the fact that dogs can run tells us nothing at all in and of itself and considered as a purely logical matter about whether or not dogs' ears can run. And it's the behaviors of quasi-isolated subsystems of the world, after all, and not the universe as a whole, that the science of thermodynamics is primarily, and in the first instance, about. And all of this, considered as a purely logical matter, is surely true, but it overlooks or it misunderstands how the Boltzmannian arguments actually work. The core of what the Boltzmannian tradition has given us is a general strategy for assigning specific numerical probabilities to any propositions whatever about the macro conditions of isolated thermodynamic systems at any time t greater than t0, given the macro condition of the system at t0. And the argument to the effect that thermodynamic systems in non-equilibrium macro conditions are overwhelmingly likely to increase their entropies as time goes forward is simply an application of that general strategy to the special case of entropies of isolated systems. The business of actually calculating these probabilities in physically interesting cases is usually going to be prohibitively complicated, but what Boltzmann and his various collaborators and inheritors are widely thought to have made plausible is not just that those probabilities are in good accord with the observation that the overall entropy of the universe is increasing, but that they're in good accord with the entirety of our everyday thermodynamic experience. If, for example, the isolated system in question consists of two gases which are initially at different temperatures and which are in thermal contact with one another, what the Boltzmannian arguments make plausible is not merely that the overall entropy of the system is overwhelmingly likely to go up towards the future, but in addition to that, that the entropy of the hotter gas is overwhelmingly likely to go down toward the future. And if the isolated system consists of, say, 12 isolated gases in 12 separate containers, each of which is initially far from its own individual equilibrium state, then what the Boltzmann arguments are going to make plausible is not merely that the overall entropy of this system is overwhelmingly likely to go up toward the future, but in addition, that the separate entropies of each of those 12 gases are all individually overwhelmingly likely to go up towards the future. Of course, the probability of the entropy of some particular one of those gases going down toward the future will be larger than the probability of the overall entropy of the 12 of them going down together toward the future. But both of those probabilities are, of course, going to be fantastically small. Good. So those are the two trivial and less interesting versions of this question. There's a third question in the general vicinity of these two, which I think is the deepest and the most interesting, and sort of the most phenomenological form of the general puzzlement about the Boltzmannian project that I mentioned at the beginning of my talk. And it's this third question, which is the one I mainly want to talk about today. Let me put this third question in four increasingly concrete and increasingly simple and increasingly tractable ways. First way, how can it seriously be imagined that my own sense of the passage of time, how can it seriously be imagined, for example, that my own sense right here and now of whether some particular baseball happens to be flying towards me or away from me is somehow anchored in the lowness of the entropy of the universe 15 billion years ago? Second version of the question, how can it be, how can it work that the increase of the entropy of the world or of myself somehow constitutes the standard or the yardstick against which I judge the direction in which events are unfolding? How is it that the entropy gradient of anything ever comes into the picture? I'm certainly not aware of checking on the entropy gradient of anything in the course of deciding whether the baseball is flying towards me or flying away from me. No comparison with anything else, insofar as I'm aware, is involved. I simply directly, unmediatedly see that the baseball is either flying towards me or flying away from me. Third version. Consider the sense of the direction of time that is implicit in the operations of, for example, a simple mechanical realization of a Turing machine. Can anyone seriously believe that the thermodynamical characteristics of the world somehow play a role in the way a machine like that distinguishes between what it has just done and what it's supposed to do next? How so? How can that be? How would that work? Machines like that can apparently function perfectly well. Machines like that apparently have no trouble at all in distinguishing between what they've just done and what they're supposed to do next, without the aid of any special devices for measuring the entropy gradient of the world or of themselves or of anything else. Fourth version, the most concrete version, the version we'll really be able to get our teeth into. Consider, finally, a simple mechanical device that has no other business than distinguishing between what it has just done and what it is supposed to do next. The paradigmatic distinguisher, you might say, the distinguisher par excellence between what it has just done and what it is supposed to do next. Think, that is, of a clock. And think, for the sake of concreteness, for the sake of simplicity, of an old-fashioned, fully mechanical pendulum clock. Good. Now we have our hands on something that we're in a position to analyze in detail. Note, to begin with, that in the course of the normal and intended operations of a clock like that, there are going to be moments, the moments in particular when the pendulum is precisely at the high point of its swing, at the apogee of its swing, when every last one of its macroscopic moving parts is for an instant completely at rest. Note, to put it slightly differently, that in the course of the normal and intended operations of a clock like that, there are going to be moments, the moments again, when the pendulum is exactly at the apogee of its swing, when the macro condition of the clock in its entirety is invariant under time reversal. You take this macro state at the moment when the pendulum is at the high point of its swing, you reduce the velocities of all the elementary particles of which the clock consists, you get the same macro state, the state where the pendulum is at rest and at the apogee of its swing. Good. And consider how it is at moments like that, that the clock manages to distinguish between what it's just done and what it's supposed to do next. The puzzle here is that at this moment, the macro state of the clock is completely invariant under time reversal. The macro condition of the clock, together with the microscopic dynamical equations of motion, together with the statistical postulate familiar from statistical mechanics, those three things are not going to do the trick. Because if the present macro condition of the clock, together with the microscopic dynamical equations of motion and the statistical postulate, makes it likely that the clock is going to read, say, 3:05, 5 minutes from now, and if the present macro condition of the clock is invariant under time reversal, then the present macro condition of the clock, together with the microscopic dynamical equations of motion and the statistical postulate, both of which are themselves invariant under time reversal, is necessarily also going to make it likely, and likely to exactly the same degree, that the clock read 3:05 5 minutes ago. There's nothing in this situation to distinguish between what the clock is supposed to do going forwards and what the clock is supposed to do going backwards. And all there is to break the symmetry, all that stands in the way of the clocks having read 3:05 5 minutes ago instead of 2:55 5 minutes ago, is the past hypothesis. The clock's ability to distinguish, that is the condition of the universe 15 billion years ago, the low entropy condition of the universe 15 billion years ago, which introduces a time asymmetry into the whole system. The clock's ability to distinguish between what it did last and what it does next, and your ability to distinguish between a baseball's flying towards you and a baseball's flying away from you, is apparently anchored in the entropy gradient of the universe. If we're to hold the present macro condition, if we were to hold, the present macro condition of the world fixed, and move the past hypothesis from the beginning of time to its end, the clock would run backwards. And that, in a nutshell, is that. But the fact is, from experience talking to people about this, people often find this hard to take in and hard to believe. Here's a nice example. Here's the reaction of an anonymous referee. I won't reveal the name, but I have some reason to believe that this referee is actually a well-known theoretical physicist. Here's the reaction of an anonymous referee to an earlier version of this paper. The referee says, "It's uncharacteristic of Albert to pass over the details. He could have described how a pendulum clock works, e.g. falling weight version, so on. He could have described how a pendulum clock works in a couple of minutes, but he didn't. The mechanism cannot run backwards. What drives it is the falling of the weight pulling on the cord. If there's no pull, the clock stops. If there's push on the cord, the clock stops. It'll only work if there's tension in the cord, and that will make the hands move clockwise because of the way the cord is wound around the drive axle. And that would be true even if the weight rose up into the air and started pulling upwards. Putting the low entropy in the future of the universe can't make the clock run backwards, as he claims. The clock knows which way to go, if it's going to go at all, because the information is built into the way that the cord is wound around the axle." And this is worth pausing over, I think, and thinking about. If one thinks it through in detail, one learns something interesting about the way the second law of dynamics functions in the world. So let me start by simply reiterating the very general point that I made a minute ago. It must be that in some way or other, what the referee is saying is mistaken. No further details about the inner workings of the clock can make the slightest bit of difference here. Consider again a moment when the clock, when the macroscopic state of the clock is stationary. Consider that is a moment when the macroscopic state of the clock is invariant under a reversal of all of the velocities of its microscopic particulate constituents. In the absence of a past hypothesis, the predictions of statistical mechanics about the evolution of the macro condition of this clock away from that moment toward the future are going to be identical to its predictions about the evolution of its macroscopic condition away from that moment toward the past, for the simple reason that there is nothing whatever in the situation to distinguish between them. In the absence of a past hypothesis, the predictions of statistical mechanics are, in particular, that as we proceed away from the present in either temporal direction, the cord is always going to be unwinding, and the hands of the clock are always going to be turning in the clockwise direction. And it's only because of the truth of the past hypothesis, because it can be only because of the truth of the past hypothesis as a matter of logic, that as a matter of actual fact, those hands turn counterclockwise as we proceed away from the present in the direction of the past. If we watch a movie going backwards. And that, again, is why a clock like this can be used as an indicator of the temporal direction in which the entropy of the universe as a whole is increasing. But the response of the anonymous referee that I quoted above, and similar responses from any number of other people who've read earlier versions of this paper, who heard earlier versions of this talk, shows that for all the brevity and simplicity and logical rigor of the argument, it leaves a stubborn and widespread atmosphere of puzzlement in its weight. It shows that something more than a meteorological proof, something more in the way of an explanation, something more in the way of a detailed story of causes and effects is called for here. And I want to try to provide a story like that over the rest of the course of this talk. So, let me begin by trying to make the character of this puzzlement, as I understand it, as vivid as I can. Consider, to begin with, a billiard ball moving freely through empty space. The motion of a ball like that certainly does not, in and of itself, and in the absence of any relevant background information about where this ball came from or how it came to be moving, it doesn't amount to a reliable indicator of the direction in which the entropy of the universe as a whole is increasing. A ball like that, after all, and given the information we have before us, could just as easily be moving to the right as to the left as time moves away from the moment of the Big Bang. But this is certainly not to deny that the evolution of the complete physical condition of a ball like this is, or might well be, a thermodynamically irreversible process. The temperature of the ball, for example, might be higher near the middle than it is closer to the periphery. And in that case, the temperature at various different locations within the ball is going to undergo a process of equilibration as its center of mass moves from one point to another. And the entropy of the ball will be changing as its center of mass moves from one point to another. And in particular, the temporal direction in which the entropy of the ball is rising is almost certainly going to coincide, by the Boltzmannian argument that I discussed before, with the temporal direction in which the entropy of the universe as a whole is rising. And so the evolution of the entropy of a ball like the one I just described will amount to a reliable indicator of the direction in which the entropy of the universe as a whole is evolving. But the evolution of the position of the center of mass of the ball is not going to be an indicator of anything like that. And the reason that both of these claims can simultaneously be true is, of course, that the entropy of a ball like this on the one hand and the position of its center of mass on the other are independent physical degrees of freedom, and that the dynamical laws of the evolution of the complete physical condition of a ball like this don't impose any connection between them. The position of the center of mass of a ball like this plays no role at all, either as a matter of definition or as a matter of dynamical law in the determination of the value of its entropy. And the entropy of a ball like this plays no role at all, either as a matter of definition or as a matter of dynamical law in the determination of the value of the position of its center of mass. Things could, of course, have been otherwise. Imagine, for example, that there were little temperature-sensing devices at various points within the ball, which transmit the results of their temperature measurements to some central processing unit, which uses those results to calculate the entropy of the ball, and which thereafter encodes the result of that calculation, perhaps by means of some sort of mechanical arm, in the position of the ball's center of mass. In the context of an arrangement like that, the temperature sensors and the central processing unit are going to amount to a device for measuring the entropy of the ball, and the output of that device will be the position of the ball's center of mass. And this is a simple and vivid and paradigmatic example of the sort of thing I have in mind when I speak of a dynamical connection between the entropy of the ball and the position of its center of mass. Good. Now, with all this in mind, consider the situation of the pendulum clock. At first glance, the relationship between the thermodynamic entropy of a pendulum clock and the position of its hand seems much like the relationship between the thermodynamic entropy of the billiard ball that we were talking about earlier, that is the first one, the one without the temperature sensors, and the position of its center of mass. The entropy of the clock and the position of its hand are distinct and independent physical degrees of freedom. And if I open up a clock like this and examine its inner workings, I'm going to find nothing that looks as if it's been designed to measure the volume or the temperature or the pressure of anything. I find nothing that looks as if it's been designed to track some process of thermodynamic equilibration and to somehow hook that up with the position of the clock hand. Indeed, insofar as the entropy of the clock itself is concerned, we know that good clockmakers go to a great deal of trouble precisely in order to eliminate any potential sources of dissipation, any rubbing or scratching or denting or heating or what have you from the clocks that they produce. And yet, and this is a way of putting what strikes us as mysterious about the operations of a clock like this, the evolution of the position of the hand somehow does manage to amount, unlike the position of the center of mass of the original billiard ball, to a reliable indicator of the direction of entropic time. The temporal direction in which the hand is advancing in the clockwise direction in space is reliably, and in the absence of any further information about where the clock came from or how it was made, the temporal direction that points away from the Big Bang. If you look at the clock and see in which direction the hands are moving, you see in which direction the Big Bang, in which temporal direction the Big Bang was. Good. The temporal direction in which the hand of the clock is advancing in the clockwise direction in space is reliably, and in the absence of any further information about where the clock came from or how it was made, the temporal direction in which the entropy of the universe as a whole is increasing. But how does that work? And I think this is what puzzles people. How can that work? How does the increase in the entropy of the world or of the clock or of anything at all even manage to get into the picture here? How does any of that ever become more relevant to the direction in which the clock hand is turning than it is to the direction in which the center of mass of the first of the billiard balls that we talked about above is moving? That, I take it, is the puzzle. That, I think, is what has the referee and many other listeners to the first half of this talk so confused. And it is, indeed, on the face of it, confusing. Let's have a look, then, at the inner workings of the sort of pendulum clock that the referee has in mind. Those inner workings, if we could put up the figure, right? Those inner workings are crudely pictured here. I stole part of this image from the internet and filled in other parts of it myself, so it's a bit messy. But anyway, let's talk about how this clock works. Note that the cord to which the weight is attached is wound around the axle in the clockwise direction, so that the axle itself and the clock hands that are attached to it rotate in the clockwise direction as the weight descends. The rest of the mechanism, the pendulum and the escapement, that is this gear and those little red tabs, the rest of the mechanism, the pendulum and the escapement, are apparently there simply in order to regulate the rate at which the axle rotates. If they weren't there, the axle and the clock hands that are attached to it would rotate more and more quickly as the weight accelerated under the influence of gravitation towards the floor. What the pendulum and the escapement do is to set a limit, call it theta, on the angle through which the axle is able to turn over the course of any single swing of the pendulum. What happens in a little more detail is this. We begin with the macro state that's depicted in this picture. The pendulum is at the apogee of its rightward swing, and as it begins to swing toward the left, the little red metal tab on the left is lifted out of the way of the gear tooth number 1, and the weight is able to exert an uncanceled torque on the axle, pulling it in the clockwise direction. As the pendulum swings toward the left, the little red metal tab on the right is lowered into the path of gear tooth number 2, and the ensuing collision stops the rotation of the axle dead in its tracks, where it is held fast by the pressure of the weight until the pendulum begins to swing back towards the right. As the pendulum swings toward the right, the little red metal tab on the left is lowered into the path of gear tooth number 3, and the ensuing collision stops the rotation of the axle dead in its tracks again, where it's held fast by the pressure of the weight, and the whole process begins over again. And what the referee seems to have overlooked, and this is the heart of the matter here, is that all of this depends crucially on the occurrence at every swing of the pendulum of phenomena like denting and scraping and heating in the operations of the escapement. For suppose that no such things, no denting or scraping or heating, no dissipative processes ever did occur. Suppose in particular that the collisions between the gear tooths and the little red metal things were perfectly elastic collisions. We begin again with the macro state depicted in the picture. The pendulum is at the apogee of its rightward swing, and as it begins to swing toward the left, the little red metal tab on the left is lifted out of the way of gear tooth number 1, and the weight is able to exert an uncanceled torque on the axle, pulling it in the clockwise direction. As the pendulum swings toward the left, the little red metal tab on the right is lowered into the path of gear tooth number 2. And in the ensuing elastic collision, the gear tooth is going to bounce off the metal tab, and the axle will completely retrace its previous clockwise rotation in the counterclockwise direction, at the end of which the little red tab on the left will be smoothly reunited in exactly the configuration shown in the picture with clock tooth number 1. And then, of course, the whole process will simply begin again, and the axle will turn clockwise by theta, and then counterclockwise by theta, and then clockwise by theta, and then counterclockwise by theta, and so on forever. And the clock will be rendered completely incapable of distinguishing between the past and the future. Good. Let's take one more look then, with all of that in mind, at the words of the anonymous referee. Let's start with this. The referee says that, quote, the mechanism cannot turn backwards. And the word cannot is in all capitals, like Trump posts emails in the middle of the night. The mechanism cannot turn backwards. But of course it can run backwards, at least insofar as the microscopic equations of motion are concerned. The microscopic equations of motion, after all, are invariant under time reversal. Anything that can happen then can also happen backwards. What's true, of course, is that the mechanism cannot run backwards without running afoul of the second law of thermodynamics. Every time one of the teeth on the wheel slams into one of the little red tabs and stops rotating, the clockwise rotational kinetic energy of the wheel is converted into heat because it has to go somewhere. Total energy is, of course, conserved. And what needs to happen in order for the mechanism to run backwards is, of course, that the heat gets transformed again and again and in its entirety into counterclockwise rotational kinetic energy of the axle. And this is, of course, in direct violation of the Kelvin formulation of the second law of thermodynamics. The referee goes on to say, putting low entropy in the future of the universe can't make the clock run backwards, as he, that is me, claims. The clock knows which way to go, still quoting the referee, if it's going to go at all, because the information is built into the way that the cord is wound around the axle. Well, let's see. Something is plainly right to begin with about the claim that the clock knows which way to go, if it's going to go at all, because the information is built into it in the way that the cord is wound around the axle. If the cord were wound around the axle in the opposite direction, after all, the clock would plainly turn in the opposite direction. But turn, and I guess this is the question that the referee forgot to ask themselves, turn with respect to what? Is it that the way in which the cord is wound around the axle determines the way in which the axle is going to turn with respect to whatever temporal direction we happen to have labeled with a plus sign? How could that be? Is it that the way the cord is wound around the axle determines which way the axle is going to turn with respect to some purely metaphysical arrow of time which makes no appearance whatever in the laws of physics? How can that be what must be the case? And what we ought to have seen all along, and what we have just now managed to spell out in full mechanical detail, is that the information that's built into the way the cord is wound around the axle is information about which way to turn with respect to the entropy gradient of this escapement mechanism here. What must be the case, and what we ought to have seen all along, and what we've just now managed to spell out in full mechanical detail, is that the information that's built into the way the cord is wound around the axle is information about which way to turn with respect to the temporal direction that points away from the Big Bang 15 billion years ago. And we can now see in particular that in the absence of dissipation, and notwithstanding the particular way that the cord happens to be wound around the axle, a clock like this is going to have no clue which way to turn. We can now see, to put it slightly differently, that in the absence of dissipation, and notwithstanding the particular way that the cord happens to be wound around the axle, the macroscopic evolution of a clock like this, not merely the laws of that evolution, mind you, but the evolution itself is going to be completely invariant under time reversal. Suppose, for example, that we were shown a movie of the operations of a clock like this one, the one we've just been talking about, that is the one with elastic collisions, turning clockwise by theta and then counterclockwise by theta and then clockwise by theta and so on ad infinitum. Nothing about the sequences of images with which we're presented, and nothing about the way that the cord happens to be wound around the axle is going to tell us anything at all about whether this movie is being run forward or in reverse. So, it's perfectly true that clockmakers take great pains to eliminate every imaginable source of dissipation from the mechanisms they produce. And they're perfectly right to do that. But it is also true, and it is, I think, a beautiful and ironical and surprising feature of the way the world actually turns out to work, that if they were ever to perfectly succeed, their clocks would become perfectly useless. It turns out that the pendulum clock is a mechanism for establishing a dynamical connection between the entropy of its escapement and the positions of its hands. This particular mechanism turns out to be much more subtle and much more circuitous and much harder to follow than the mechanism we discussed above, the one that consists of the temperature sensors and the central processing unit and the mechanical arm that connects the entropy of the billiard ball with the position of its center of mass. But this mechanism ends up imposing exactly the same kind of connection. And it does so in a way that seems to have been a complete mystery, even to the most accomplished and revered designers of the clocks that make use of this. And so, to make a long story short, this is just the beginning of the suggestion of a project, but I guess my suspicion is that something very much along these lines must be what's explaining how a typical realization of a Turing machine knows the difference between what it did last and what it does next. And it seems to me that once all of this has been taken on board, the atmosphere of mystery around, say, my own ability to sense the difference between a baseball flying towards me and a baseball flying away from me, to sense it, mind you, immediately and without any conscious active inference and without my brain ever being aware of checking on the entropy of anything, just like there's nothing in this clock that's specifically designed to check on the entropy of anything. It seems to me that once you go through this clock example in detail, the mystery surrounding my ability to tell the difference between a baseball's coming towards me and a baseball's going away from me begins to melt away. But of course, one wants to know much more about this situation. And I hope that kind of work will be done in the future. Thank you.